Hello, AP Chem. Today we are going to be talking about taking care of stoichiometric problems when you have chemicals that are in the aqueous form. So we're going to be talking about solution stoichiometry and how to deal with problems like this. And I would say that of all the stoichiometry types that we run into, this is the one that students tend to have the hardest time with. So I want to kind of show you both potential ways that we could be doing a stoichiometry problem and go through a couple examples and try to troubleshoot where we run into problems, because it really is kind of a fundamental thing that they're going to ask you questions about, and you got to be good at it. So we're going to do a little bit of practice. So like I said, what happens is in chemistry, there are tons of chemical processes and reactions that happen in solution. So you've got aqueous reactants, or they need a water-based environment for them to happen. And so we're going to have to use a calculation using molarity instead of just a mass-to-mass calculation or something like that. Later on, we're going to be getting into gas stoichiometry questions, but I think those personally are easier than the molarity, and people tend to make less mistakes with those. But the process that we use with a molarity stoichiometry problem stays the same. It's just that because there's this molarity component, people tend to kind of flip out a little bit. So just like before, you need to balance your equation, then get your starting information into moles. If you have a molarity given to you, remember that M times V always gives you the moles of that solution as long as the volumes are in the same units. So whether your volume and your molarity are in liters or in milliliters, as long as they're the same, you should be good to go. But remember that, get your starting information into moles, then convert to moles of what you're solving for using your mole ratio, and then you solve for the correct units. So everything is the same. It's just that you could potentially run into a couple different situations. So we're just going to go straight to examples because you guys know how to do stoichiometry. I just want to do a couple practice problems with you. So for the first one, it says how many milliliters of 1.0 molar nitric acid, which is HNO3, is required to react with 100 grams of cuprous oxide, which is the copper 1 oxide here. So we're going to take a look at this. When we look at these problems, this is where people kind of freak out a little bit. I've seen people do a number of things where they try to use masses here instead of using the molarity. But if you have a molarity in your problem, you kind of have to use the molarity. So we're going to go to, I'm going to escape out of here. And we're going to go to my DocCam, and I'm going to work on that problem with you. So if you want to, let me just kind of go back here. If you want to pause and give this problem a try, or get this problem written down, you can, and then I'm going to present it on my little notepad here. So it starts off in our problem that we have 100 grams of the Cu2O. So the cuprous oxide that they call it. Now, in this case, because we have our starting information into grams, you should know and be professionals at getting this into moles. So for every 1 mole of Cu2O, it weighs 143.1 grams. That's just 2 coppers and an oxygen put together. And that gets us into moles of what we're starting with. Now we're starting with copper 1 oxide, or cuprous oxide they call it, and we're solving for nitric acid, which is HNO3. So if you looked back to our starting problem, there are 14 moles of HNO3 for every 3 moles of Cu2O. Okay, so when we think about our problem here, it's asking us to figure out how many milliliters of a certain molarity solution we are solving for. So we are looking for, in this case, some milliliters or some sort of volume that you need to figure out for this problem. So if you think about where our units are right now, grams and grams are canceled out. Moles of copper oxide and copper oxide are canceled out, and we are currently in moles of HNO3. We have not used our molarity, the 1.5 molar HNO3 yet. And so what we need to think about is what this M means. If you recall, 1.5 molar actually means 1.5 moles of HNO3 per liter or per 1,000 milliliters, either way, depending on what you're solving for. So you could write that as liters, or we could write it as 1,000 milliliters. You have to pick one though. You can't like leave this in the problem. So when you think about molarity can be used vertical in its normal way like this, or we can invert it and use the liters on the top and the moles at the bottom. Molarity is just another conversion factor that we have kind of in our pocket here. So if you think about how we're going to solve this problem, we need to figure out what the volume of this acid is that we are going to need here. But we have to get rid of the moles of HNO3. And so to do that, we need to use that molarity, but we need to invert it, and we're going to put the 1.5 moles of HNO3 on the bottom so that our moles of HNO3 cancel out, and then we are solving for volume. So if we're solving for liters or milliliters, you can put either or there. I believe we're solving for milliliters. So I'm going to put 1,000 milliliters on the top here. So what I'm doing is I'm actually using the molarity, but I'm taking advantage of the fact that the molarity is kind of its own conversion factor here. So it's moles over liters, or vice versa. I have seen people in the past just try to like divide. They get stuck by thinking that this M is a static unit, but the M is 2 units, and it's going to help you kind of keep things canceled out. So if I take all these things, I'm going to take 100 grams times 1 divided by 143.1 times 14 divided by 3 times 1,000 divided by 1.5. I end up getting 2,174 milliliters. And so that comes out to be 2.174 liters of my HNO3 to completely react this, which if you think about it, feels like a lot, but there's a lot of chemical here. We have almost a whole mole, and you need quite a bit more of the HNO3 than you do for the copper 1 oxide. So that is how you would deal with it if you were dealing with grams and then you were solving for a volume. Okay, now the other problem, let me get to it, example 2 here. Okay, so you're going to want to pause and write this down, and if you want to give it a try ahead of time, go ahead. Otherwise, we're going to work through it right away. So in this one, you have a 25 milliliter, 0.35 molar NaOH sample, and that's added to a 45 milliliter, 0.125 molar copper 2 sulfate solution. So we're going to mix those two things together. And then this is a precipitation reaction. We are going to get copper 2 hydroxide as our precipitate. Balanced equation is there for us, 2 NaOH to 1 copper sulfate, and it's going to make copper 2 hydroxide and Na2SO4. So it's saying if I've got these two things that I'm mixing together, how many grams of stuff am I going to precipitate? And then it also says to draw a beaker showing all the species present after the reaction is complete. And by species, they mean chemical species. So like what chemicals are floating around in there? Okay. Now, when you look at this problem, and again, you can pause the video at any point if you need to copy this down in your notebook. When you look at this problem, what's different than the previous problem is if you look here, I've got information about my copper oxide, the cuprous oxide, and then I'm solving for the other thing here. So in this case, I'm solving for my nitric acid. In this problem, we've got a different kind of setup because I have the volume and molarity of the NaOH, and I have the volume and the molarity of a copper 2 sulfate solution here. And we are solving for a product. So this problem here, as you read this, hopefully you recognize that in the previous problem, I just had one of these and I'm solving for the other reactant. In this problem, I have both reactants and I'm solving for a product. So this is actually a limiting reactant problem. And that's why we're asking questions about what the beaker is going to look like afterwards. So get this problem copied down. If you want to try it out by yourself, you can go ahead and go for it. If not, I'm going to work through it right now and then we will give a look at it. Okay, so you know that I personally prefer to do limiting reactant problems where we solve for the thing that we are looking for right away. So I'll do 2 lines of stoichiometry. So what I'm personally going to do is I'm going to start off with my NaOH, and then I'm going to do stoichiometry to my copper 2 hydroxide, and then I'm going to do that again for the copper 2 sulfate. So starting off here, I have 25 milliliters of my NaOH. And we know that we always want to get our starting information into moles, right? Well, if you remember, M times V gives you moles of that thing. So it's 25 milliliters of NaOH, and I'm going to multiply that by the molarity of that NaOH, and that is 0.35 moles of NaOH. And then this is where you can put in over either a liter and convert this to liters before you get started. Or, like I said, if I'm feeling kind of like I know what I'm doing and I don't feel like doing the converting, I will write the molarity like this instead, just to take care of my units. So what happens is when I take my molarity times my volume, I end up getting the moles, which is what we want to do. So we're going to get our starting information into moles. Then we are going to go to our mole ratio. So in this case, for every 2 moles of NaOH, I'm going to produce 1 mole of CuOH2. Okay, and then we're going to solve for what it's asking for, and it's asking for grams of this copper 2 hydroxide. So I've got to figure out the molar mass of that. And 1 mole of copper 2 hydroxide weighs 97.566 grams. So when I go through and I do my stoichiometry and taking care of the dimensional analysis, check my units, everything cancels out and I'm left with grams of the copper hydroxide here. So if I take 25 times 0.35 divided by 1,000 divided by 2 times 97.566, I get 0.427 grams of the copper 2 hydroxide. Okay, so what we need to do then is we need to repeat that for the copper sulfate, the CuSO4. So if you didn't know how to do it initially, why don't you pause the video and duplicate this calculation for the copper sulfate? We're still finding the same thing, the copper hydroxide, so why don't you pause the video, work it out yourself, and then see if you can figure out how much copper hydroxide is actually going to be produced. Okay, hopefully you got that figured out. To start off, we have 45 milliliters of the copper sulfate. And if you want, like I said, we could convert this into liters if you wanted to. I don't, just because I know that I can write it like this for 0.125 moles of CuSO4 over 1,000 milliliters. And then those will cancel out and it's the same thing. So I'll do the moles of what I'm starting with, which is the copper sulfate. And then I need to go to the same precipitate copper hydroxide here. And in this case, it's 1 mole of CuSO4 for 1 mole of CuOH2. So it's a 1-to-1 mole ratio instead of a 1-to-2 mole ratio. Now, because I'm solving for the same precipitate, I'm going to have 97.566 grams for every 1 mole of the copper 2 hydroxide. And if I put this into my calculator, I get 0.548 grams of the copper 2 hydroxide. So we've got 2 masses of the same thing here. If you think about the problem, it's asking me how much could get made. So in this case, because it's a limiting reactant problem, I am going to make the lowest amount, which is going to be 0.427 grams of that copper hydroxide. And that means that the NaOH is my limiting reactant. It means that my copper sulfate is going to be my excess. Okay, so when you think about your reaction here and your net ionic equation, our net ionic equation is going to be Cu plus 2 hydroxides turning into CuOH2. And if we put our phases, we've got aqueous, and solid. Okay, so we've got our setup here. It's asking us to draw a picture of what we've got in our beaker. So again, keep in mind, I'm going to rewrite it over here. NaOH is our limiting reactant. CuSO4 is our excess. And then we got our reaction here. So at the bottom, we're going to have our solid, and our solid's going to be that copper 2 hydroxide. Now we got to think about what's floating around in there. So in terms of quantities of stuff, we are going to have Na as a spectator ion and the sulfate as a spectator ion. And if you think about them floating around in there, I'm going to have some Na pluses in there. Okay, I'm going to have some sulfates in there. Floating around as well. Now, if you notice, I did put in one more Na, and that's because if we think about the quantity of the actual stuff in there, like the actual moles of stuff that are in there, if I take 25 times 0.35, I am going to get more moles than I am of the sulfate here. So that's where I'm getting that from. I don't know if that's going to be a huge deal, but that's something we can talk about in our meet if we have any questions about that. The bigger issue is, what are we going to have extra of? Since we do have a limiting and an excess situation here, we've got to think about, are we going to have any copper floating around or any hydroxide? Now, if you think about the limiting reactant is going to be the hydroxide. So that means that in this equation here, the thing that's going to run out is going to be the hydroxide because it's a limiting reactant. So what we're going to actually have is a tiny amount of copper plus 2 floating around in there as well. So I'm going to have a lot of Na. And again, if I wanted to do that, I could figure that out. I'm going to do this on the fly here because I'm unprepared. Na would be 25 milliliters times 0.35 moles for 1,000 milliliters. So if I take 25 times 0.35 divided by 1,000, I'm going to get 0.00875 moles of the NaOH floating around in there. Okay. For my CuSO4, if I take 45 milliliters times 0.125 moles for every 1,000 milliliters, I get 0.005625 moles. So if we think about what's floating around in there, the reason why I have more Na in solution is because I actually start off with more moles of sodium hydroxide. Now you say to yourself, Adi Meyer, this doesn't make any sense because you told me NaOH is a limiting reactant. And that's correct, it is. And the reason why it's a limiting reactant is because of the 2-to-1 mole ratio. So even though I start off with more moles of NaOH to start off with, because I need 2 moles of them to make 1 mole of copper hydroxide, I end up making less precipitate. Okay, so what you could potentially be asked to do is to draw a drawing with the relative amounts in there, and then you'd have mostly Na plus a little bit of the sulfate in there, slightly less, and then a teeny tiny amount of the copper that's floating around in there, and that's because the copper is the excess. So most of the copper is trapped in this copper 2 hydroxide precipitate, but a little bit of it is left floating around in the beaker. I have seen problems like this on the multiple choice. I have seen them where you've had to do a beaker drawing. So I guess, just keep those things in mind as you go along. All right. If you have any questions, please make sure you get those things cleared up. Otherwise, good luck.